Decision trees are very good at capturing the relationship between attributes and labels in a training dataset. We saw a glimpse of how that happens in um, the previous lectures, right? So this comes with a problem actually. The problem is that it might overfit on the training dataset. So in order to avoid the overfitting, we should aim to build simpler and thus more compact trees that can generalize better in for unknown or unseen examples, right? In order to build compact trees, we cannot just choose to split on any random attribute, right? We must split on those attributes specifically that give the most information gain with respect to the labels of each of the examples. If we choose our splitting attributes in that respect, we'll be able to get or form trees that make less splits overall, and ultimately it will make the overall tree more compact. So we should actually shift our focus now to on how to choose the best attribute for splitting while learning a decision tree. Now let's try to visualize or understand what do we mean by a good or best attribute. In a previous example, to determine if one should admit a student into a university or not, we had seen the attributes CGPA and GRE to be the distinguishing factors, right? And in that example, we had randomly chosen CGPA to be the first attribute that we split our decision tree on, right? As you can see on the slide, I've brought in the previous decision tree that we had formed. However, if we look at the features or attributes individually, we see a different picture. So now let's see these attributes individually. So for CGPA, we have actually drawn an illustration for the split of CGPA at 3.8, right? This is the split. So if we split at 3.8, we can see that in the data set we have one example which is greater than equals to 3.8, right? This one. And the label of the example is yes. So we give a positive sign for it. For less than 3.8, we have two examples. For one, the label is yes, so we give a positive sign for it. And for another, the label is no, so we give a negative sign for it. Similarly, when we observe GRE individually, we see that there are two examples in the dataset which is greater than 320 score, and for both of them the labels are yes, so we give positive sign for each of them. And there is only one example where the GRE score is less than 320 and the label is no for that, right? Now if we observe the distributions together, we see that if CGPA is greater than equals to 3.8, we can directly say that the student should be admitted. So the label will be yes. On the other hand, if it is less than 3.8, one is yes and another is no, right? So there is a mixture, right, in this distribution. But for GRE, if GRE score is greater than 320, we can conclusively say that the student should be admitted, and if the GRE score is less than equals to 320, we can conclusively say that the student should not be admitted to the university according to this data set. So for GRE, we can come up with a conclusive answer, right, for each of the classes of GRE. But on the other hand, for CGPA, if CGPA is less than 3.8, we have to look at the second attribute, which is GRE. So if the CGPA is less than 3.8, but GRE score is greater than 320, the label is yes. But if CGPA is less than 3.8 and GRE is less than 320, the label is no. So we have to split our decision tree twice. If we split it, choose CGPA to be the root node, right? But if we choose GRE to be the root node, we can conclusively say that if GRE score is greater than 320, the label will be yes. If it is less than 320, the label will be no. So using GRE as the root node or as the first attribute to be splitted on, we actually need less number of splits. But as you can see in the previous example, where we had used CGPA to be the first node, first attribute to split on, we actually needed to split twice. So there were two levels of the decision tree, one level and the second level, right? So we can see that if we choose a better attribute, in this case, this is GRE, we can actually make the decision tree much smaller and more compact. Since we can come up with conclusive answers using GRE, we say that the GRE distribution is more pure than the CGPA attribute. And purity, conversely, impurity is actually measured in terms of entropy, which is an information theory concept, which we will look at in a bit. Okay. But before that, here's another example of how to distinguish if an attribute is more or less pure than the other. So if we see both these distributions, we can easily observe that the distribution on the right hand side is more pure and the distribution on the left hand side is more impure than the right. So we should choose to split on an attribute that is more pure than the other one, right? That is the most pure one. So we should choose to split on whether applicant is employed or not in this case. However, for more complex examples, it is not as easy to distinguish as to which feature is more impure than the other, right? So for example, if there were more examples here, more positives, more positives, more positives here, and then there were some circles here, positives here, we wouldn't really be able to distinguish properly uh, which of these two distributions is more impure, right? So uh, we actually need to quantify or a numeric value to calculate the impurity in a specific distribution. And entropy does that specific thing. As I mentioned earlier, entropy is a concept from information theory, which actually helps us measure the level of impurity in a group of examples or a distribution. So higher the impurity in a distribution, higher is the entropy value.